All right. For me, it's in the evening, but hello, everybody. Welcome to Organic Chemistry 2. This is going to be the final part for the videos regarding test 1 because it's coming up. It's going to be next Thursday, and I'm really trying to help you guys get the last of this material out because we are not going to be slowing down. We will be getting into some synthesis and then some naphthalene reactions and then some more reactions. It's just never ending, essentially. But this is supposed to help make sure you guys can backtrack and have a solid foundation as we move forward. All right. Now I'm going to share my screen. I should see this. Great. Okay. So for benzene derivatives, it follows a little bit of wonky rules, but I promise once it makes sense, it makes absolute sense. And I'll be going over some topics and I'll be backtracking a little bit, but trust me, just watch it until the end and it'll come full circle, essentially. Okay. So just to start from the beginning, our OrthoMetaPara directors, those are 3 types of locants on a benzene ring. And usually that's in a relative position compared to your substituent. Your substituent being your electrophile. So like if you have a normal benzene ring and you for some reason, or for, yeah, I guess for a reason, you somehow get a nitro group on it. All right. So you now have nitrobenzene. That is now your E group. Your electrophile was that nitro group. And now you were to, let's do nitrate. Let's say we nitrated again. Okay. If we nitrated again, and where would it go? Would it go in the ortho, meta, or para? That's why our locants are important. So just to review, anything that's, ooh, erase that. I'm sorry. Ooh. That E is supposed to be ortho. Ortho is always 1 carbon away from your substitution group. Meta, it's going to be 2 carbons away. And directly across is going to be para. All right. And I want to bring up a compound that we've already used before. So if you remember semester 1 during our oxidation reaction, we have this compound called MCPBA, lowercase MCPBA. You're thinking, why is M lowercase? Well, MCPBA is actually metachloropyrbenzoic acid. So if I were to draw it out for you guys, it looks something like this. Metachloropyrbenzoic acid, where you have your E group, your perbenzoic acid, not something you have to know. And meta to that is a chloro group. So we've actually already seen one of these types of compounds in one of our stuff or one of our reactions before. This is pretty handy. Well, it's not pretty handy. It's just pretty cool. Now, let's look at activating groups, OrthoMetaPara, all that stuff. So is there a clear-cut relationship? Do all activating groups become orthopara? Do all deactivating groups become meta? The answer is straight up no, it does not. If you look at the chart down here, that is provided for you, but not on the test, but it is given in test 1 study materials. You have all of the activators being orthopara directing, and then the deactivators being meta directing, with the exception of your halogens, which are weak deactivators, but orthopara directing. How the hell does that happen? Well, hopefully this video will go over why. And all of the answers lie in resonance structures. Okay. So how should you go about, well, knowing activating deactivating groups? Well, activating groups are always electron donating. Electron donating. So if they're electron donating, then that E is trying to put electron density into the benzene ring. Let me draw that in black. Electron density is going into the benzene ring. All right. And deactivating groups, well, it's obviously the opposite. It's going to be electron withdrawing. Electron withdrawing. So your E group, your electrophile, or that you were looking at, your substituent, will be putting or pulling electron density away. And I like to think of it as an electron sink. All right. It's pulling electron density away from the ring. So how do we see that? Well, I'll get to that later. Orthopara, though all electron donating groups are orthopara, I like to think of orthopara as if it has a lone pair. If E has a lone pair, All right, it's going to be ortho pair directing. And that's, I'll give you a little bit of a hint. And that's because when you break the the aromatic ring in electrophilic aromatic substitution, all right, ortho and para, I'll show you later, will always have the carbocation form on that electrophilic, well, not the electrophilic, but the carbon that bears the electrophile, or the former the carbon that bears the substitution group will always be on that carbon. So if you have a lone pair, it can always donate for that existing positive charge and make another pi bond, which is extremely stable if you remember our resonance rules. Again, I'll go over it in detail later, but just a little bit of a heads up. Just go over again. If your I gotta stop saying electrophile. If your substituent E has a lone pair, it is ortho-para. And that applies for all of this. All right. Aniline. Right. N and H2. There's a lone pair. It's electron donating. The deactivators. Cl. No, there's no formal charge. There's a lone pair. So it might not be electron donating because it's actually very electronegative, and a pi bond between that and the positive charge carbocation is not very good, which again, we will get to. It's not very stable, it's deactivating, but the fact that it's has alone pairs means it's ortho-pair directing. All right. Conversely, let's bring it back. Conversely, meta directing, I don't know, I missed the A. Meta directing means that your substituent has a positive charge or a partially positive charge. All right. So usually what that means is, okay, if it bears a positive charge, it cannot make another pi bond with that future positive charge. All right. Excuse me. It cannot make another pi bond. It's partially positive or positive formal charge. Look over here. All right. Let's take aniline. The moment you protonate aniline into NH3 plus, all right, there's no more lone pair because that lone pair was used as a nucleophile or to perform a nucleophilic attack on a proton. So the moment it's protonated, you no longer have a lone pair on that nitrogen. There's a positive charge on it. You can't do anything. So it's now a strong deactivator. All right. Ooh. So I'm just going to recap what I just said. Okay. So in detail, activating groups are, well, yeah, activating groups are all ortho-para. All right. They all have lone pairs. So activating groups, electron donating. All right. All activated groups are ortho-pair directing. They're electron donating. They always have that lone pair. So when they have that, or when they contribute resonance into that aromatic ring, partially negative, they're pushing density into the ring. All right. Conversely, if you have, let's say, our Y, not actually an element, but just variable Y, if it's, let's say, in this kind of structure where that oxygen is pulling electron density away, partially negative, this is going to have a partially positive charge. Well, it's an electron sink. It's pulling density away from the ring into that partially positive charge. This is electron withdrawing. All right. So let's dab a little more. So this forms resonance that donate to the aromatic ring. While electron withdrawing draws electron density away from the aromatic ring. How is this relevant? How the hell is this relevant? Well, let's start from the left. So if it's electron donating and it's pushing electrons into the aromatic ring, well, if the electrons are being pushed into the aromatic ring, well, it speeds up the reaction. All right. Not only that, well, the aromatic ring, if the electron density is being pushed into it, is relatively electron rich. And what this does is that it also provides stability, extra stability, for continuous conjugation. It stabilizes those resonance structures. That's essentially what I'm saying with all of these 3 points. It's stabilizing the resonance structures. And again, I will show that later. So you'll see this firsthand, like when I show you. So don't worry about this right now. Now, conversely, if it's electron withdrawing, slows down or retards the reaction. All right. So again, you have a deactivator, of course, going to slow it down, right? Now, the atom, let's say the atom Y, whoops, is directly attached to the aromatic system, okay? Again, the atom Y is going to be partially positive or positive formal charge. This is the density is being pulled away. So, resonance will place a positive charge on that alpha substituent. So again, the carbon that bears the substitution group, when you have an electrophilic aromatic substitution, you have a positive charge in that aromatic ring. So you put it near that already partially positive or positive formal charge Y, 2 positive charges near each other, that's not very stable. So, okay, here, near E, our alpha substituent. So the conjugated pi system will spill over and be destabilized. Remember, our conjugated pi system for aromatic systems. Conjugated pi system spills over and is destabilized. Okay, so remember, aromatic rings, you have a continuous conjugated pi system. And if electron density is being pulled away out of the ring, it's destabilizing that entire ring system. On the contrast, it is donating, it's speeding up that conjugation system. So it's really stable, right? Now, let's go into electrophilic aromatic substitution. Something you might also see is something like this. That's the same thing. It's like, all right. It's kind of like our SN2 reactions. So, electrophilic aromatic substitution, all right? SN2 would be, I think, nucleophilic bimolecular substitution, but this one is electrophilic aromatic substitution. Okay, so to go over the mechanism real quick, let me get the right note out. All right, I got the right notes out. You guys should still be seeing my screen. So for electrophilic aromatic substitution, what essentially happens is we have a benzene ring and we react it with some kind of reagent that we will have to memorize, and you'll eventually just basically slap on or replace one of the hydrogens with your electrophile. So remember, benzene, you have hydrogens attached, C6H6. You're essentially just replacing one of those hydrogens with your electrophile. So how the hell does this happen? Well, to go over the mechanism, the double bond breaks and attacks your electrophile. Because your electrophile, well, it's in the name, it's electrophilic, is attracted to, electrons. Well, what's the aromatic ring but a ring of electrons? So it'll attack the electrophile, and the bond that's between your would-be anion, your nucleophile, that covalent bond goes then to your anion. So just to redraw it out, when that happens, your rate determining step, because once you break that bond, remember your rate determining step is your bond breaking step, essentially the formation of your carbocation, to form something like this. He, positive charge, H. And all these H's are still here. H. Okay. So you have that plus your nucleophile with that residual negative charge. Okay. How the hell does this contribute to our OrthoMetaPara stuff? Well, if you look right here, look at that. You can form resonance structures. Wow. So if you form resonance structures, look, you can door hinge over here and basically analytic exchange or something like this. Now I'm going to omit the hydrogens for simplicity's sake. I just drew a hydrogen. For simplicity's sake. You can door hinge again, form resonance structure once again. So now you have something like this. All right. Well, these are all resonance structures. So what does the hybrid look like? The hybrid would look at something a little like this. E. Then you have a positive charge being shared among everything else. All right. So let's look at the energy diagram. All right. Energy diagram wise, this is energy. This is going to be time. Well, if you're starting at the beginning, you're reacting. Remember, your biggest hump is your rate determining step. It requires the most amount of energy. And you have two humps because you have an intermediate. The carbocation intermediate is an actual state of matter. It's not a transition state. And then again, when we have the elimination. All right, so this right here, this is our rate determining step, our reactants, and our products. Now, come back to here. What is this step right here? Well, we're not finished yet. We have to look at the next part, which is our elimination. So essentially what will happen is whatever hydrogen that positive charge is attached to, your nucleophile will come back in, basically swoop that up, and that the electrons on that covalent bond between your carbon and your hydrogen will go back and reform into that aromatic ring. So that'll form an elimination reaction. Or you'll have something like this. Now in pink, I'm going to draw the reformed double bond from that original covalent bond. And now you have your nucleophile and that H. I don't know why I drew an H over here. I don't know why I keep doing that. Pretty late. There you go. So you basically just substituted one of the H's with an E, your electrophile, right? So now let's look at the resonance structures. Okay, I redrew this out. Okay, so real quick, just for context, when we nitrate something, nitration is an electrophilic aromatic substitution, where with HNO3, nitric acid, and sulfuric acid, we add a nitro group to it, a nitro NO2. That's the group we're adding. So if we're reacting aniline, now let's make it CH3. Yeah, let's make CH3. If we're reacting, no, I should do it as aniline. Where's the Lewis base? Sorry, I'm trying to think of a really good example for you guys. I apologize. You know what? I just decided I'll get to it later. So we'll keep it as a toluene, and then I'll get to a chlorobenzene later. Okay, so nitration, we're nitrating it, so we're trying to add an NO2 group. So now let's look at the different positions of those resonance structures if we reform. Because remember, in the mechanism I showed you guys above, there are 3 resonance structures. You door hinge twice because you have your initial carbocation, door hinge over, second carbocation, door hinge over, third carbocation. So let's break this first one. So if you add the electrophile right here, that complex, if you were to form an ortho product, right? This is going to be your initial one. Your initial, I'm going to keep in pink. E, positive charge there, and these are original CH3. Let me zoom in. Okay. So essentially what I did was if it's ortho to our substituent, then I'm breaking that double bond that's, well, in the ortho position because I can't attach the E here. So again, just ortho, carbon right next to one carbon away from your substituent. So I break that double bond. And I have a positive charge right there. Well, already I know that's tertiary. That's tertiary. So now let's draw some resonance structures. So resonance-wise, we have a door hinge maneuver Positive charge here, ECH3. Okay. Let's redraw this. This. And our E's are NO2, CH3, positive charge here. We have secondary, secondary. Okay. Now, if we were to do a para, we were to have that E attach here. Okay. Oh, shoot. All right. This should be recording. I had some technical difficulties as well as personal difficulties because I changed all the E's back into NO2s. And I thought I forgot to miss a point or to make a point, but I didn't. So crisis averted. Okay, back to where we were. Let's say we were trying to do para. Okay, so for para, let's say we were trying to attach our substituent right there and we break that double bond. So we're to break that double bond, it would look something like this, where we have our NO2 here, positive charge here, and our still residual rest of our aromatic toluene. Okay, resonance structures. Let's redraw it. Door hinge maneuver over, we get positive charge here, CH3, NO2. Another resonance structure. Okay, here, NO2, positive charge here, CH3. Let's look at those carbon-cation stabilities. We have secondary, tertiary, secondary. Great. Now let's do it one last time with our metagroups. So our metagroups, there we go. So for our metagroups, if we were to break that double bond and put that electrophile on the meta position, let's break that double bond, we would form something that would look like this. NO2, keep the rest of the aromatic toluene, positive charge right here. All right, so now let's draw our other two resonance structures that we can form. NO2, door hinge again, form resonance structure that looks like this. NO2, CH3. Okay. So if we have this, let's look at our carbon-cation stabilities, secondary, secondary, secondary. You look at that. So this is the main differentiation I wanted to make. Your ortho and your para groups, they have a tertiary carbocation. Well, that's if it's toluene, but what if it was aniline? Still, nonetheless, those carbocations right here fall on the same carbon that's bonded with your substitution group. That's the main distinction I wanted to make. While in contrast, your meta group, those carbocations in no position at all is on the same alpha carbon as your substituent. And that is what's super important. Because, okay, imagine, remember, our deactivating groups. Our deactivating groups are electron withdrawing. And our meta directors are always going to have a positive charge or a partially positive charge on the atom that's directly attached to the aromatic ring. So if, excuse me, if the the atom that's directly attached to the aromatic ring is partially positive, it would make sense that we want meta because of the positive charge, no matter what in either position, is not directly attached to it. This is what I'm trying to say. So if, let's say we had a protonated aniline, remember, NH3 plus is a strong deactivator. It looks something like this. It's aniline, but protonated. So there's a positive charge on the nitrogen. So if we were to follow our meta rules, if we were to add something that's meta, then our carbocations would form only here. And if they form only there, well, our hypothetical positive charges are nowhere or not directly close to that nitrogen. And conversely, if we were to look at our OrthoPara, our OrthoPara puts the carbocations right here, hypothetically. So if we were to follow the OrthoPara, well, we're putting two positive charges next to each other. That's not stable at all. Nitrogen and all the other main deactivators are pulling electron density away from the aromatic ring. So it makes sense that we don't want to put the positive charges from the resonance structures on that constituent carbon. So that's why we want it to be meta, because if we were to spare it and just keep in the meta position, well, those positive charges aren't anywhere near our electron sink. So that brings me to this part, activating compounds and deactivating compounds. You might be thinking, why the hell am I bringing this up now? And I didn't talk about it earlier up there. Well, I wanted to get the definitions down for activating groups and deactivating groups up here. And now that I've shown you what those resonance structures look like, now let's try to tie them all together and just pay attention. Okay, so our strong deactivators are going to be, let me zoom in. Strong deactivators are going to be, in order, NH2, NHR, and this is kind of not on the chart, but this is also like NR2, so it could be like a dimethylamine, OH and OR. OR being another R group being an ether, right? So let's take a look. This is what that original benzene ring would look like. So let's do an oxygen, for example, right? Remember, our OrthoPara groups would have the positive charges on those resonance structures right here. You might be thinking, wait, isn't oxygen electronegative? You might be thinking, yes, but remember, if it's OrthoPara is directed by lone pairs. So if that substituent has a lone pair, like oxygen, if it donates that lone pair, it has an extra resonance structure. So I'm going to just really quickly draw the resonance structures that we formed from a phenol reaction. So resonance structure 1, if you were to have, let's say, an ortho group, let's do OH, let's add NO2, positive charge here, here. Another resonance structure. Positive charge here, NO2, OH. I'm going to zoom in for you guys. There we go. Nope. It's not gonna let me zoom in further. I'm sorry. All right. Search here, NO2, OH. Now, because you have a lone pair, you can make another resonance structure. Lone pairs can donate and put electrons into the aromatic system. There you go. You have something like this. Positive charge here, lone pair still, NO2. Now, this goes to show the fact that you can make a fourth resonance structure if that substituent atom has a lone pair is the reason why we want OrthoPara products. So going back up to here, look at all of these compounds that are OrthoPara directing. They all have lone pairs. So when you have those the main three resonance intermediates that are in electrophilic aromatic substitution, the fact that it has a lone pairs that can donate, it can make another resonance structure. Not only that, that resonance structure adds a pi bond. And if you remember from your resonance structure stability, the first thing you look at is the number of pi bonds. Automatically, out of all the resonance structures, the compound that has the most pi bonds is the most stable. All right. It's the most stable. So going back down to here, okay. We have this. We have 4 resonance structures, and that's why our activators, because they all have lone pairs, they can make extra resonance structures. And we like OrthoPara because, again, OrthoPara gives us the positive charge on that substituent carbon, and thus we can make more resonance. And another point I would like to make is, well, why is aniline over oxygen? Oh, come on. Right? This is more activating than OH. Why is that? Well, if you look at aniline, all right, nitrogen, H2, And lone pair's gone. This is that resonance structure that we would see for aniline. If, we nitrated aniline, I don't know if that's, don't worry about it yet. But if we nitrated aniline, right, we had an ortho nitro group and we have a positive charge that originally went to here. But we used the lone pair in aniline to make another pi bond. Now, out of the resonance structures between these two in particular, let me use a bigger highlighter, right? Between these two, which one's more stable or which one's more favorable? It would be the aniline one, because remember, nitrogen is more electropositive than oxygen. Nitrogen can better hold a positive charge than oxygen. Hence, it's more activating than oxygen because it is able to contribute more into the aromatic system. It's more activating. And that brings me to our moderate activators. You have your N terminus of your amide and your O terminus of your ester. Now you're thinking, what the hell is an amide? What the hell is an ester? Well, an ester, something like this. Carbonyl carbon, like a ketone or an aldehyde, but you have an O. And an amide is the same exact thing, but instead of an O, you have an N. Let's say that's just an H off to the side. Right? And something I want to note, these have lone pairs. Well, these carbonyl carbons are partially positive. So depending on what portion is connected to your benzene ring, depends on, or is what makes a strong, or not strong, moderate activator or deactivator. So what do I mean by this? So if it's the N terminus of your amide group, this is what you would see. A benzene ring with N, lone pair, H, connected to a carbonyl carbon. Let's just say it was a simple CH3. Same thing with the ester. We have something like this. Carbon, CH3. The O terminus, not, yeah, I'm gonna leave that here for now, not the C terminus. So the fact that it's attached through the nitrogen or the oxygen means that it has, look at that, lone pairs. The lone pairs, when we're doing resonance structures, if it's OrthoMetaPara, we put the positive charges here. And the lone pairs can thus donate and form more resonance structures, which is why it's more favorable. All right. Now, for your weak activators, that's just your any alkyl group, like a methyl group or an aromatic ring. That's kind of it. Why is that? Well, hyperconjugation, and if it's another aromatic ring, you can have a continuous conjugated pi system. It's same exact reasons. Now, let's look at our deactivating compounds. I'm actually going to take this and copy. Nope, not cut. Copy it. Let's see if my paste will work. Oh, nice. Okay, great. So among our moderate deactivators are the C terminus of our amides or our esters. Okay. Now you might be thinking, what does C terminus mean? That means it's attached on that carbonyl carbon that's partially positive rather than our oxygen and our nitrogen with lone pairs. So let's go ahead and draw that. So among our bottom two is the C terminus of an ester. So C OR, and the C terminus of an amide, NHR. So the benzene rings that would see that are stuff like this. So like, there you go. All right. That benzene ring is directly attached to this carbon, and that carbon is partially positive. So if you were to have our OrthoPara carbocations, well, look at that. We're putting a positive charge near partially positive. That's not very stable. In contrast, if we had a meta, right, meta situation, we would have positive charges being spread out away from that partially positive charge. All right. Now let's look at our weak deactivators. This is our kind of our niche group that kind of break the rules a little bit because they're both very electronegative. They're deactivating the ring. They're deactivating because they're pulling electron density out of the ring. They're electron sinks. But at the same time, they have lone pairs that can hypothetically form resonance structures. So resonance-wise, ortho-para resonance structures are favored. So those products would form. Granted, it'd be very slow because it's kind of deactivated, but the pathway is still there. The stars align for it to be ortho-para. You feel? So this includes all the halogens. All the halogens, just as it is on the periodic table. So you have fluorine. Let me draw them as their benzene rings, or how you'd see them benzene ring. Fluorine, fluorine, bromine, and iodine. What if I said iodine? Dr. Geller says iodine. All right, activating is it this way. So iodine is more deactivating than fluorine. So fluorine is the least deactivating. All right, so all of these have lone pairs. So if I were to draw, let's say, chlorobenzene, if I were to react it with electrophilic aromatic substitution, if I were to make nitro chlorobenzene or add a nitro group to that, we would have an original initial structure that looks like this. And O2, let's say it was ortho. Positive charge, Cl, like this. Now, we can make two other resonance structures just from the double bonds in the aromatic ring. We've already covered that. But chlorine can donate lone pairs. We can make a structure that looks like this. Now, I'm just going to go ahead and draw them to the side. Just so you guys see it. Cl. Now this fourth one, I'm going to put a little star next to it because that's the one of importance, is this. We can make a fourth resonance structure just like our other activating groups. Because remember, all of our activating groups have a lone pair, with the exception of the CH3 and the aromatic rings. But they have lone pairs that they can donate and contribute to resonance structures. So do all the halogens. The halogens have lone pairs. So because of that, here, our ortho and para carbocations are favored, not the meta. However, I do want to reemphasize, because it's a halogen, it's deactivating. It's still pulling electron density out of the ring. So our strong deactivators, going back to our moderate deactivators, follow the same exact rules. So I'm going to finish the rest of the list. So the other moderate deactivators are going to be our aldehydes, COH, and ketones, COR. All right, essentially a carbonyl carbon is partially positive. So all of your moderate deactivators, all right, all of your moderate deactivators, they are just partially positive. Among this, let me bring this down a little bit. Benzoic acid, that's the one I forgot. That's my bad. CO, and then it's just OH. Yeah. But those carbonyl carbons are partially positive. So you want the meta positions, because the partially positive, it doesn't want to be adjacent to, it does not want to be adjacent to a positive charge that would arise from an ortho-para. Now, strong deactivators, these usually have an extremely strong positive, partially positive charge, or straight up a positive charge form or positive formal charge. So our strong deactivators are going to be our nitrile group, sulfonic acid, ammonium group, and then a nitro group. All right, and let's see what they look like. So this is what our nitrile group looks like. Nitrogen is partially negative, carbon is very partially positive. It is extremely partially positive. So it does not want to be anywhere near that positive charge during electrophilic aromatic substitution. Same thing with benzene sulfonic acid. All right. You have sulfur, boom, boom. Sulfur is partially positive. And then for NH3 and NO2, those nitrogens, straight up, they have a positive formal charge. I already showed you aniline, or the protonated aniline, where that lone pair is lost and becomes a hydrogen. Positive charge. And for nitric group, positive charge. Looks like that. Here, let's redraw it. So just to re-emphasize that our deactivators, aside from our halogens, they want meta because they don't want to be near that positive charge. So if we have, let's say, benzoic acid. Let's say we were trying to put a nitric group on it. Let's put another nitric group on it. So I know for a fact, okay, our benzoic acid, if I know my chart, is a electron withdrawing group, and it's meta-directing. All right. How do I know it's meta-directing? Well, the atom that's directly attached to the aromatic ring is partially positive, so I know it's meta-directing. Not only that, it is electron withdrawing because you have a partially positive charge. That's electron sink is pulling electron density out of it. Okay, we're trying to add a nitric group onto it. Our initial structure would look like this. OH. NO2, positive charge here. Okay, let's form our resonance structures. Okay, these are all of the resonance structures that I can make. If you look at that, those positive charges, they're all on secondary carbons. They're nowhere near on the direct carbons that are connected to that carbonyl carbon, because again, it's positively charged. If I were to, for example, let's say, follow the OrthoPara directing group. So let's make a different hypothetical branch over here, NO2. Let's do benzoic acid again, OH. And I put a nitric group, that's ortho. Positive charge here. Let's draw the resonance structures. There we go. 2 H L 2 LH. Look right here. Look at that. Positive charges are now here. But this is the big no-no because you have a partially positive charge on that carbonyl carbon. Positive charge next to partially positive charge. That's extremely unstable. That's not what we want. And that's what's general for all of our weak deactivators. Now, something I want to make note of, I think, where are my notes? In my TA notes, I might post this along with the announcement I'm about to make. But these are like my condensed notes per se, right? So this will be available for everyone. This is essentially what I just talked about. And this shows where that electron sink is. Like for this one, you have the carbonyl carbon in your moderate deactivators, just pull electron density away from it, which is meta-directing, because you don't want your positive charge to be on that, to be anywhere near that carbonyl carbon. So now let's use what we just learned about for this. So for the question, which is more acidic? All right. We always love to bring back acid bases. So which of the following is more acidic? Now, I might split the video right here. Yeah, I'm actually going to just stop the video and we'll just get into practice.